In this video, we're going to look at how to calculate the theoretical and the percent yield. These values are important in chemistry for discussing chemical reactions and how efficiently they proceed. In general, the amount of product you can get in any chemical reaction is going to be dependent on the limiting reactant. We looked at how you determine the limiting reactant in the last video, and in this video, we're specifically going to be talking about the amount of product that you can form based on that limiting reactant. The theoretical yield is the most product that you can possibly make, and it assumes that there's no experimental errors and no losses of your materials. The actual yield, on the other hand, is what you actually would observe in the lab. That might result from something like spilling or just the reaction not fully going to completion. In general, the actual yield should be less than the theoretical yield. The percent yield is then the quantification of the difference in that actual and theoretical yield. And because we talk about it as a percentage, we just multiply that value by 100. And the only thing to be careful of here is that your yield values are reported in the same units because you have to have the units cancel. Let's look at how we would calculate these values using the following example. Iron oxide can be reacted with carbon monoxide to produce iron metal and carbon dioxide. We're given a balanced chemical reaction and told that we have 152 grams of iron oxide, 84.6 grams of carbon monoxide, and we're also told that we have 68.2 grams of iron that is produced at the end of the day. And this is the actual yield. So you can calculate the actual yield given a theoretical yield and a percent yield, but more often this is something that you would measure in the lab and you would just determine experimentally. So given this information, we need to find the limiting reactant, the theoretical yield, and the percent yield. So to find the limiting reactant, we need to know how much product we can form. I'm going to start off with my grams of iron oxide, and I need to convert that into moles of iron oxide, which from there I can determine how many moles of iron are produced. And at this point, I would be able to compare with what's produced using carbon monoxide. For the carbon monoxide, I would also start with grams, because that's what I was given in the problem. I would need to convert to moles, and from there, I can determine the number of moles of iron using the stoichiometric relations given in the chemical equation. Once I've determined the number of moles of iron that can be made from each of my starting materials, I'll know which is the limiting reactant, and therefore the theoretical yield. So I'm going to go ahead and start plugging in my numbers. So I have 152 grams of iron oxide, and I'm going to convert that into moles using the molar mass. Using a periodic table, I find that the mass of an iron atom is 55.85 grams per mole. The mass of an oxygen is 16 grams per mole. And so I need 3 oxygens and 2 irons, which gives me a total mass of 159.7 grams in 1 mole of iron oxide. To convert from iron oxide to iron, I need to use my stoichiometric ratio, which is 1 mole of iron oxide for every 2 moles of iron. At the end of the day, this gives me a total of 1.90 moles of iron. On the other hand, if I start with my carbon monoxide, 4.6 grams, the molar mass ratio I want to use here is 28.01 grams per mole of molecules. And now I need to convert from carbon monoxide to iron, again using a stoichiometric ratio. So in this case, I have 3 moles of carbon monoxide for every 2 moles of iron. And I need the moles of carbon monoxide in the denominator and the moles of iron in the numerator so that everything cancels. And this gives me a total of 2.01 moles of iron. So these values are fairly close. It's only a difference of about 0.1 moles, but the smaller one is coming from the iron oxide. So the iron oxide is our limiting reactant. So we've answered the first question, which is the limiting reactant. The theoretical yield is going to come directly from the amount of product produced by the limiting reactant. In this case, we're going to start with 1.90 moles of iron, but we're asked for the theoretical yield in grams. So again, we need to make use of our atomic mass for iron, which is 55.85 grams per mole, and we need moles in the denominator in order to cancel with the moles that we start with. And so we would have a total of 106.1 grams. So this is my theoretical yield, although I should really only have 3 significant figures. So when I report my final answer, I want to make sure that that's all I report. Finally, we're asked for the percent yield. To find the percent yield, we need to take our actual yield divided by the theoretical yield and multiply that by 100. So the actual yield was given in the problem as 62.8 grams, and we would divide that by 106.1 grams and multiply by 100, and computing this value gives 59.2%. So this would be the percent yield. And now it's your turn. Here's a problem for you to practice with. The solution for this one is actually in the textbook, so you can use that to check your work. But make sure you give it a try on your own first. Happy practicing.